Three ants are walking in the same direction. The first ant has two ants behind him, the second ant has one in front and one behind. But the third ant has one in front and one behind too. How is this possible? Let me explain the solution now. The most widely accepted and logical answer to this riddle is the ants are moving in the same direction but in a circular manner, not in straight line. Let's say the ants are A, B, and C. A has B and C behind him, B has A in front and C behind, and C has B in front and A behind. In this way, third ant has one in front and one behind too. There can be other solution to this riddle. Do share yours in the comment section. But the most widely accepted answer to this riddle is the ants are moving in a circular manner. Suppose we have 3 glasses and 10 coins. The problem is to place odd number of coins in each glass. That is, each glass should contain coins and the number of coins in each glass must be odd and total coins which will be used must be equal to 10. Let me repeat the puzzle. Suppose we have 3 glasses and 10 coins. The problem is to place odd number of coins in each glass. That is, each glass should contain coins and the number of coins in each glass must be odd and total coins which will be used must be equal to 10. See, it is not possible to use all 10 coins with each glass having odd number of coins. This is because if you add odd number of coins odd number of times, then the result is always odd but not even. But here there are 10 coins which is even. That is the challenge here. There are even number of coins but number of glasses are odd. Therefore, we must think out of the box. Let's solve now logically. So in the first step, in the first glass, place 5 coins which is odd. After that, in the second step, in second glass, place 2 coins, and in the third step, in third glass, place 3 coins which is odd. Here the first glass contains 5 coins which is odd, second glass contains 2 coins which is even, and the third glass contains 3 coins which is odd. Now is the important step. After third step, glass 1 has 5 coins, glass 2 has 2 coins and glass 3 has 3 coins. Now place the entire third glass inside second glass. By doing this, we are making sure that the second glass has 5 coins. Hence, indirectly, now second glass contains 5 coins which is odd in nature. As shown in the image, there are 9 dogs within a fence. By constructing just 2 more square fences, can you make sure that each dog is in isolation? Let me repeat the puzzle. As shown in the image, there are 9 dogs within a fence. By constructing just 2 more square fences, can you make sure that each dog is in isolation? If you are struggling to get the answer, let me explain the solution now. It might seem tricky at first, but there is a very simple way of working out the real answer. To solve this riddle, one just needs to draw a diagonal square and a straight square inside it. First, let's draw a diagonal square. Now, draw a straight square. As we can see now, by constructing just 2 square fences, each dog is in isolation. This is one of the most interesting riddle which requires out of the box thinking to achieve the correct answer. There are 100 doors in a row. All doors are initially closed. A person walks through all doors multiple times and toggle. which means if door is open, then close. If door is closed, then open. Person does this in following way. In first walk, the person toggles every door, that is first, second, third, fourth till 100th door. In second walk, the person toggles every second door, that is second, fourth, sixth, eighth, so on till 100th door. In third walk, the person toggles every third door, that is third, sixth, ninth, 12th, so on till 99th door. In other words, person toggles all doors which are multiple of 3. If person performs these operations, you are supposed to find which doors are open in the end. According to the problem statement, in first walk, the person toggles every door, that is first, second, third, fourth till 100th door. Hence, after the first walk, every door is open. In second walk, the person toggles every second door, that is second, fourth, sixth, eighth, so on till 100th door. Hence, on the second walk, person only visits the even doors. So at the end of second walk, the even doors are closed and the odd ones are opened. In third walk, the person toggles every third door, that is third, sixth, ninth, 12th, so on till 99th door. In the third time, person will close door 3, opened from the first pass, open door 6, closed from the second pass. And person will close door 9, opened from the first pass, open door 12, closed from the second pass, and it repeats. A door is toggled in nth walk if n divides door number. For example, consider the door number 45. So 45 door is toggled in first, third, fifth, ninth, 15th and 45th walk because these are the numbers which divides 45. So the door is switched back to initial stage for every pair of divisors. For example, 45 is toggled 6 times for 3 pairs, that is 1, 45, 3, 15 and 5, 9. So on walk 1, person will open the door. In walk 3, he will close it. Walk 5, he will open it. Walk 9, he will close it. Walk 15, he will open it. Walk 45, he will close it. So for every pair of divisors, the door will just end up back in its initial state, that is in the closed state. So let's consider one more example. Say door 42. Person will visit it for every divisor it has. So 42 has 1 and 42, 2 and 21, 3 and 14, 6 and 7. So on pass 1, person will open the door. On pass 2, he will close it. Pass 3, he will open it. Pass 6, he will close it. Pass 7, he will open it. Pass 14, he will close it. Pass 21, he will open it. And pass 42, he will close it. So for every pair of divisors, the door will just end up back in the initial state. So it looks like all doors would become closed at the end. But there are door numbers which would become open. Example door 9. So 9 has the divisors 1 and 9, 3 and 3. But 3 is repeated because 9 is the perfect square. So you will only visit door 9 on pass 1, 3 and 9, leaving it open at the end. Only perfect square doors will be open at the end. So the answer is all perfect squares, that is 1, 4, 9, 16, 25, 36, 49, 64, 81 and 100. These are the doors open in the end. A prisoner is faced with a decision where he must open one of two doors. Behind each door is either a lady or a tiger. They may be both tigers, both ladies, or one of each. If the prisoner opens a door
to find a lady, he will marry her, and if he opens a door to find a tiger, you will be eaten alive. Of course, the prisoner would prefer to be married than eaten alive. Each of the doors has a statement written on it. The statement on door 1 says, in this room there is a lady, and in the other room there is a tiger. The statement on door 2 says, in one of these rooms there is a lady, and in one of these rooms there is a tiger. The prisoner is informed that one of the statements is true and one is false. Which door should the prisoner open? Let me explain the solution now. As per the puzzle, each of the doors has a statement written on it. The statement on door 1 says, in this room there is a lady, and in the other room there is a tiger. The statement on door 2 says, in one of these rooms there is a lady, and in one of these rooms there is a tiger. Let's analyze the statements now. For a moment, let's assume that first statement is true. That is, the lady is behind the door 1 and tiger is behind the door 2. But this makes statement 2 also true, where it says there is tiger behind one of these doors and lady behind one of these doors. Hence, the statement 1 can't be true. Hence, statement 2 must be true. As per the second statement, only possibilities left are: first possibility, door 1 tiger, door 2 tiger; second possibility, door 1 lady, door 2 lady; and the third possibility is door 1 tiger, door 2 lady. As per the second statement, in one of these rooms there is a lady, and in one of these rooms there is a tiger. Since the true second statement is suggesting there is lady behind one door and tiger behind the other door, the possibilities of both tigers or ladies are eliminated. The only remaining option is door 1 tiger and door 2 lady. That's why behind door 1 is tiger and behind door 2 is lady. Thus prisoner must open door 2 for survival.
Once there was a king. The king wanted to protect his kingdom from the outside world. So he made a rule that neither any citizen of the kingdom can go to the outer world nor anyone from outside can enter his kingdom. There was a common bridge between the kingdom and the outside world. The guard was assigned on the gates of the kingdom, which was linked to the bridge. If anyone tried to go out of the kingdom, he or she will be killed. And if anyone tried to come inside the kingdom, the guards would send them back. It takes 8 minutes to cross the bridge. The guard was allowed to take a 5 minutes break. One woman was able to cross the bridge and move to the outside world. How did she do that? Let's check the solution now. As per the puzzle, there is only one common bridge through which anyone can enter to the kingdom or leave from the kingdom. Total time taken to cross the bridge is 8 minutes, and guards are assigned to the bridge to monitor. There is no way to cross the bridge without guards' notice, since total time required to cross the bridge is 8 minutes, but the guard was allowed to take maximum of 5 minutes break. The time when the guard was at rest, if the woman starts to walk towards the outer world, she will be caught after 5 minutes and will be killed. This is because, as per the king's order, if anyone tried to go out of the kingdom, he or she will be killed. And if anyone tried to come inside the kingdom, the guards would send them back. The solution to this puzzle requires out of the box thinking. Let me explain now how women could be able to cross the bridge from the kingdom. The time when the guard was at rest, the woman will start to walk towards the outer world. She will walk for 5 minutes and then will turn back towards the kingdom. Since she had no document with her, she was not allowed to come inside the kingdom. Now guards think that the woman is trying to enter the kingdom. Therefore, the guards sent her outside the kingdom. Hence, she was able to leave the kingdom. So this is how woman will make a plan in order to escape from the kingdom. If you have not understood the solution, please do watch again. So the trick is simple. Immediately, the time when the guard was at rest, the woman will start to walk towards the outer world. She will walk for 5 minutes and then will turn back immediately towards the kingdom. When the guards come back, they think that the woman is trying to enter the kingdom, not escaping from the kingdom. Therefore, the guards sent her outside the kingdom instead of killing her. Hence, she was able to leave the kingdom. An Arab sheikh tells his two sons to race their camels to a distant city to see who will inherit his fortune. The one whose camel is slower will win. The brothers, after wandering aimlessly for days, ask a wise man for advice. After hearing the advice, they jump on the camels and race as fast as they can to the city. What does the wise man say? So let me repeat the puzzle. An Arab sheikh tells his two sons to race their camels to a distant city to see who will inherit his fortune. The one whose camel is slower will win. The brothers, after wandering aimlessly for days, ask a wise man for advice. After hearing the advice, they jump on the camels and race as fast as they can to the city. What does the wise man say? The wise man tells them to switch camels. Let's check how this will work. Each son owns a camel. Let's call them Camel A and Camel B. If Camel A is slower, son A gets the fortune. If Camel B is slower, son B gets the fortune. Neither of the sons wants to enter the city first because they won't get the fortune. When they switch camels, son A is now riding his brother's camel, Camel B, and son B is riding his brother's camel, Camel A. Now they each want the camel they are riding to get to the city first. If son A wins the race on Camel B, that means his camel, that is Camel A, was slower and he wins the fortune. The same is true for the other way around if the second son wins the race on Camel A. Thus, the suggestion given by the wise man is tell them to switch the camels so that the task will be completed soon. A car has 4 tires and one spare tire. Each tire can travel a maximum distance of 20,000 kilometers before wearing off. So what is the maximum distance the car can travel? You are allowed to change the tires using the spare tire unlimited number of times. This is basically a condition. So the condition says you are allowed to change tires using the spare tire unlimited number of times. And there is one more important point to remember, that is all tires are used up to their full strength. So I will read it again. A car has 4 tires and one spare tire. Each tire can travel a maximum distance of 20,000 kilometers before wearing off. So what is the maximum distance the car can travel is the question. The conditions are you are allowed to change tires using the spare tire unlimited number of times, and also all tires are used up to their full strength. Let's check the solution now. See, what it is basically telling is a car has 4 tires and one spare tire. So you have a 4 tires. So I'm calling it the tires as T1, T2, T3 and T4. And there is a spare tire. I'm calling this spare tire as S1. So what you are supposed to do is divide the lifetime of spare tire into 4 equal parts. That is 5,000 and swap it at each completion of 5000 kilometers distance. What the idea is, instead of running 20,000 kilometers at one instance, so what you are supposed to do is, for an every 5000 kilometers, you are replacing the existing tires with a spare tire. So how it is going to help is, let's do the calculation now. So the first time, the first 5000 kilometers you are running with the original tires that is being attached to the car, that is with a T1, T2, T3 and T4. So after completion of 5000 kilometers, so you are replacing T1 tire with a spare tire S1. So now the T1 capacity is already 5000 kilometers, which is completed, and T2, T3, T4 have already completed 5000 kilometers. Now S1, which we have added, its capacity is still 20,000 kilometers. So now you will run for another 5000 kilometers. So with this condition, you will run for another 5000 kilometers, and after completion of 5000 kilometers, what you are supposed to do is, you are put T1 back to its original position and replace T2 with S1. Now the T1 has still 15,000 capacity and T3 has 10,000 capacity, T4 has 10,000 capacity and S1 still has 15,000 capacity. So and again continue the same procedure, like run it for another 5000 kilometers, and after completion of another 5000 kilometers, now replace the S1 with T2 tire and replace T3 with S1 tire. So now the T1 has 10,000 capacity and T2 still has 10,000 capacity and S1 has 10,000 capacity and T4 still have 5,000 capacity. So next continue the procedure and finally put T3 back to its original position and replace T4 with S1. So after completion of this particular step, all the tires maximum capacity, which is 20,000, is being fully utilized. So if you count the total number of kilometers that you have ran, so that will be 25,000 kilometers. So that would be the answer of this puzzle. So I will summarize the solution now. So divide the lifetime of spare tire into 4 equal parts, that is 5000, and swap it at each completion of 5000 kilometers distance. In the first step, so with the tires T1, T2, T3 and T4 run for 5000 kilometers, and in the next step replace T1 with S1. At 5000 kilometers replace T1 with S1, and at 10,000 kilometers put T1 back to its original position and replace T2 with S1. At 15,000 kilometers put T2 back to its original position and replace T3 with S1, and at 20,000 kilometers put T3 back to its original position and replace T4 with S1 and run for another 5000 kilometers. So in this way you can utilize all the tires capacity and the solution will be 25,000 kilometers.
In a one-day international cricket match, considering no extras, no wides, no no-balls and no overthrows, what is the maximum number of runs that a batsman can score in an ideal case? I will repeat the problem. In a one-day international cricket match, considering no extras, no wides, no no-balls and no overthrows, what is the maximum number of runs that a batsman can score in an ideal case? So note here we assume ideal and little practical scenario. We assume that batsman cannot run for more than 3 runs in a ball, as otherwise there is no limit. He can run infinite runs theoretically in a ball as far as opposite team does not catch the ball. So we are assuming that the maximum run batsman can run is 3 runs per ball. So let's check the solution now. So the basic rule of a one-day international cricket match is the total number of overs in a one-day international cricket match is 50 overs, and on each over bowler bowls 6 balls. So for an ideal case, the batsman will hit a 6 on each ball, but if he hits 6 on the last ball of the over, the strike will change in the next over.
So which means in an ideal case, the batsman will hit a 6 on every ball. But as we know about the rules in cricket, if he hits 6 on the last ball, that is 6th ball of the over, the strike will change in the next over and it will go to his partner. Thus, the best he can do in the last ball is make 3 runs so that he retains his striking position even in the next over. The total runs that a batsman can score in each over is 6 into 5 plus 3, that is 6 runs on first 5 balls and 3 runs in the last ball of the over, which will yield 33. The most important point to remember in this case is this way it has to go till the 49th over and not in the 50th over. So in the last over basically he can hit a 6 in the last ball as well because that will be the last ball of the match. Thus runs for the last over will be 6 into 6, that is 36. Hence the maximum number of runs that a batsman can score in an ideal case is, that means every over the first 5 ball is going to hit 6 and the last ball will be 3 runs, and this will continue till the 49th over. So the total number of runs a batsman can score till 49th over is 33 into 49. And in the 50th over he is going to hit 6 on all the balls, hence the last over score will be 36, which is 33 into 49 plus 36, which is going to yield 1653. So I will repeat the solution once again. So the total number of overs in a one-day international cricket match is 50. Now a batsman can score a maximum of 6 runs in each ball. But if a batsman scores 6 in the last ball, then the strike gets changed and the other batsman faces the ball. So the maximum run in the last ball can be 3. So in every over, a batsman can score 33 runs. So in 49 overs, the total score can be 49 into 33, that is 1617. In the last over, he can score 36 runs because now there is no need to change strike. So in the last over, the maximum runs can be 36. So therefore, the total score will be 1617 plus 36, which is equal to 1653. So the maximum runs a batsman can score in a one-day international cricket match in an ideal case is 1653. A lady got kidnapped by a gangster. The gangster puts 2 bullets in consecutive order in an empty 6-round revolver, spins it, points it at her head and shoots. She is still alive. The gangster then asked her, "Do you want me to spin it again and fire, or pull the trigger again right away?" The question is, which option should be preferred? For each option, what is the probability that she will be shot? The most important point here to consider is that the bullets were loaded adjacent to each other. There are 6 ways to arrange the 6-round revolver with consecutive bullets. These are the possible scenarios which can be arranged with the 2 consecutive bullets. But the first shot went blank and hence the last 2 possibilities are of no use. We can easily eliminate these possibilities. Let me explain this in detail. As per the puzzle, gangster already shot once and it is blank. This implies that in the combinations first value cannot be B, it must be X, which is empty. Hence the combination starting with B must be eliminated. So now the 4 possible arrangements of the consecutive bullets considering the first blank attempt are these. Now looking at these possibilities, our odds of getting shot are 1 by 4 or 25%. This is the only combination she will get shot. In all other combinations, the immediate one is blank. Since there are 4 combinations, in only one combination she is getting shot, it is 1 by 4 or 25% of the possibilities where she gets shot. If he respins, then following are the combinations. As we can see here, there are 2 possibilities out of 6 combinations where lady will be shot. Looking at these possibilities, our odds of getting shot is 2 by 6 or 33%. So she should prefer pulling the trigger again right away, which is 25% possibility of getting shot, instead of respin, which increases to 33% of getting shot. This is the solution for this puzzle. Suppose you have a regular hexagon made up of matchsticks with 3 diagonals in it. The task is to convert the given hexagon into 3 equilateral triangles by moving only 4 matchsticks. Before actually getting into the problem, let me explain what are hexagon and equilateral triangle. A hexagon is a 6-sided 2-dimensional geometrical figure. The total of the internal angles of any hexagon is 720 degree. A regular hexagon has 6 rotational symmetries and 6 reflection symmetries. All internal angles are 120 degrees. An equilateral triangle is a triangle in which all 3 sides and angles are equal. All 3 internal angles of equilateral triangle measure 60 degree. Let's get into the puzzle now. Here is a regular hexagon made up of matchsticks with 3 diagonals in it. The task is to convert the given hexagon into 3 equilateral triangles by moving only 4 matchsticks. Let me explain the solution now. Solution can be achieved by moving 2, 4, 5, 6 numbered matches to get exactly 3 equilateral triangles. First, move matchstick 4 adjacent to matchstick 7. Next, move matchstick 6 adjacent to matchstick 8. Next, move matchstick 5 and connect to matchstick 6, and it forms the base for the part of the triangle 3. Finally, move matchstick 2 and connect to matchstick 4 and 5, which forms the complete base for the triangle 3. Now we can clearly see that there are 3 equilateral triangles. 2 triangles are formed with side equals single matchstick, whereas third triangle formed with sides 2 matchsticks. A father wants to divide his 17 luxury cars among his 3 sons. According to the father, the older son should get half of the luxury cars, the middle son should get 1/3 of the luxury cars, and the youngest son should get 1/9 of the luxury cars. When the father died, his sons were not able to divide the luxury cars as the result was coming in fractions. As the sons were fighting on how to divide the luxury cars, a traveling mathematician driving by his luxury car came and heard their problem. He proposed a solution with which all the sons got their share in the property without destroying any car. What was the advice given by the traveling mathematician, and how the group of luxury cars was divided? Let's check the solution now. Well, this puzzle is interesting. You have to think such that with the solutions everybody is happy and nobody suffer any loss. Let's see the problem first. We have 17 luxury cars to be divided among 3 sons with the ratio as given in the problem statement. As per the problem statement, the oldest son should get half of the luxury cars, hence first son will get the half of the luxury cars, that is 17 by 2, which results in 8.5, which is a fraction. And as per the problem statement, the middle son should get 1/3 of the luxury cars, hence second son will get the 1/3 of the luxury cars, that is 17 by 3, which results in 5.66, which is again a fraction. Finally, the youngest son should get 1/9 of the luxury cars. Hence, third son will get the 1/9 of the luxury cars, that is 17 by 9, which results in 1.88, which is again a fraction. As we can see, all the results are in fraction, so the luxury cars cannot be distributed like this. So what will the traveling mathematician do to solve it? Think outside the box to solve these puzzles. This is a simple puzzle. The traveling mathematician adds his luxury car to the group of luxury cars. As we can see in the puzzle, the traveling mathematician also traveling in a luxury car. So in total, we have 18 luxury cars now. Now let's see the scenario again. As per the problem statement, the oldest son should get half of the luxury cars. Hence, first son will get the half of the luxury cars, that is 18 by 2, which results in 9. This time it is not a fraction. And as per the problem statement, the middle son should get 1/3 of the luxury cars. Hence, second son will get the 1/3 of the luxury cars, that is 18 by 3, which results in 6. Finally, the youngest son should get 1/9 of the luxury cars. Hence, third son will get 18 by 9, which results in 2. So if you count, there are 17 cars. So in total, 17 luxury cars will get distributed among the 3 sons, and the traveling mathematician will take his luxury car and leave.
A man fell in a 30-meter deep well. In one day, he climbs 4 meters up and slips 3 meters down. How many days would it take for him to come out of the well? Let me repeat the puzzle. A man fell in a 30-meter deep well. In one day, he climbs 4 meters up and slips 3 meters down. So in this case, how many days would it take for him to come out of the well? On first day, man climbs 4 meters up and slips 3 meters down, which means that on first day in total, man climbs only for a meter. Similarly, on second day, man climbs for another 4 meter and slips 3 meters down again, which means that on second day, total distance man climbs is 2 meters. This infer that the man climbs 1 meter in total each day. So like this, on 26th day, you would have climbed 26 meters. The interesting part comes on the 27th day. And on 27th day, he will climb 4 meters again. So on 27th day, man climbs full 30 meters because on 26th day, he already climbed 26 meters. And remember, on 27th day, man will not slip since he is already out of the well. This is the place where many candidates fail to analyze the problem. Many candidates will answer this as 30 days, which is incorrect. Think logically and you can easily solve this problem without any difficulties. Thus, in this puzzle, a man climbs a total of 30 meters in 27 days. He will be out of the well on 27th day.
A blind man is alone on a deserted island. He has 2 blue pills and 2 red pills. He must take exactly 1 red pill and 1 blue pill or he will die. How does he do it?
Let me explain the solution now. There are multiple solutions to this puzzle. The first and probably the most accepted answer is break each of the pills in half. As you do this, pop one half in your mouth and lay the other half aside for tomorrow. When he has done this with all four pills, he will have consumed one red pill and one blue pill and have the same left over. Practical considerations are the only issues here. Can you break the pills? For example, will they break in half exactly? The setup is sufficiently weird, or rather abstract, that I think we are entitled to make these assumptions. The second way to think is you could dissolve all the tablets in water, maybe. Drink off the glass. The first answer is generally accepted one, but there is nothing wrong with dissolving in water answer. It has its own problems, for example, assuming that the pills are water soluble. Another way to think about this puzzle is this is taken from Cora, assuming that the pills cannot be cut in half or dissolved. You could set them apart from one another on a smooth, flat rock or a large leaf. Allow the sun to shine on them for a while and then use the tip of your nose, which is very sensitive to heat, to ascertain the temperature of each pill. The red pills will feel slightly warmer than the blue pills because red colors absorb more UV radiations than blue colors do. Take one warm pill and one cool pill and you are good to go. So there can be other solutions. Do share yours in the comment section. Consider a two-player coin game where each player gets turned one by one. There is a row of even number of coins and a player on his turn can pick a coin from any of the two corners of the row. The player that collects coins with more value wins the game. Develop a strategy for the player making the first turn such he never loses the game. Note that the strategy to pick maximum of two corners may not work. In the following example, first player loses the game when he uses strategy to pick maximum of two corners. Example in this row of numbers 18, 20, 15, 30, 10, 14. First player picks 18 because it is maximum. Now row of coins is 20, 15, 30, 10, 14 and the second player picks 20. Now row of coin is this. First player picks 15 because it is maximum and the row becomes 30, 10, 14. Second player picks 30, now row becomes 10, 14. First player picks 14 because it is maximum and the second player picks 10 and the game is over. When you count, the total value collected by second player is more than compared to the first player. So the second player wins and hence this is not the right strategy. So what should be the strategy for the player making the first turn such he never loses the game? Let's check the solution now. So the whole idea is to count sum of values of all even coins and odd coins, compare the two values. The player that makes the first move can always make sure that the other player is never able to choose an even coin if sum of even coins is higher. Similarly, he can make sure that the other player never able to choose an odd coin if sum of odd coins is higher. So let's understand this with an example. Consider the same example that we have considered earlier. That is the row of numbers are 18, 20, 15, 30, 10 and 14. So this is how the coins are arranged. So first of all, count sum of values of all even coins and odd coins. Sum of all odd coins in this example is 43 and sum of all even coins in this example is 64. Since the sum of even coins is more, the first player decides to collect all even coins. So according to the strategy, he first picks 14. Now the other player can only pick a coin 10 or 18. Whichever is picked to the other player, the first player again gets an opportunity to pick an even coin and block all even coins.
For example, here, if the first player picked 14, since it's an even coin, and if the second player chooses 18 or 10, so again the first player gets an opportunity to pick the even coin. The similar strategy is applicable if the sum of odd coins is higher than the sum of even coins. This is how we have to make a strategy for the player making the first turn such he never loses the game.
There are two candles of equal length and of different thickness. The thicker one lasts of 6 hours, the thinner 2 hours lesser than the thicker one. Ramesh lights the two candles at the same time. When he went to bed, he saw the thicker one is twice the length of the thinner one. How long ago did Ramesh light the two candles? It is given that thicker one lasts 6 hours, so after each hour, 1 by 6 of the candle is melted. Thinner one lasts 2 hours lesser than thicker one, that is, it lasts 4 hours. So after each hour, 1 by 4th of the candle is melted. Logically, after 1 hour, remaining portion of the thicker candle is 5 by 6 and remaining portion of thinner candle is 3 by 4. After 2 hours, remaining portion of the thicker candle is 4 by 6 and remaining portion of thinner candle is 2 by 4. And after 3 hours, remaining portion of thicker candle is 3 by 6 and remaining portion of thinner candle is 1 by 4. Here we can notice that after 3 hours, the remaining portion of the thicker candle is 3 by 6, which is 0.5 or half. Remaining portion of thinner candle is 1 by 4, which is 0.25 or quarter, which is basically the thicker one is twice the length of the thinner one. Therefore, the answer is 3 hours.
You are standing before two closed doors. One of the doors leads to heaven and the other one leads to hell. Two watchmen are standing, one in front of each door. You know one of them always tells the truth and the other always lies. But you don't know which watchman tells the truth and who is the liar. You can ask only one question to one of them in order to find the way to heaven. What will you ask? Let's check the solution now. The solution to this puzzle is you should go to any one of the watchmen and ask him, if I ask the other watchman about which side leads to heaven, what would he answer? If you ask a direct question, which door leads to heaven, then the honest one will tell the truth and the liar watchman will point toward the door that leads to hell. But here we are not asking the direct question, we are asking one watchman about how the other will answer. Let me explain how this particular solution holds good for this situation. If you ask the honest watchman how the other, that is liar, will answer, he knows that the liar will point towards hell. So he will tell you that the answer will be the hell's door. If you ask the liar watchman how the other, that is honest, will answer, he knows that the honest one will point towards heaven door, but since he is a liar himself, he will tell you the other door, which is the door of hell. Hence, in both the cases, irrespective of whether the watchman is honest or liar, he is pointing to the hell's door. So you can choose the other path to continue your journey to heaven. Thus, instead of asking direct question, you can achieve the solution by asking indirect questions to watchmen. Having an infinite supply of water and two containers, one for 3 liters and one for 5 liters, how would you measure 4 liters? You have to follow these steps to solve this puzzle. In the first step, fill 3 liters bucket completely. In the second step, pour that water into 5 liters bucket. In the step 3, now 5 liters bucket filled with 3 liters of water where there is space for 2 more liters. Now in the step 4, now again fill 3 liters bucket and pour it into 5 liters bucket. If bucket was full, that means remaining water in 3 liters bucket is 1 liter. In the step 5, pour that 5 liters of water down and fill it with 1 liter of water which was remained in the 3 liters bucket. In the next step, again fill 3 liters bucket and pour into 5 liters bucket. Now the result will be 4 liters of water in 5 liters bucket. This is how we can achieve the solution to this particular puzzle, but there is an easy solution with less steps. Let me explain the way to solve these bucket questions. You can get 4 liters by pouring 1 liter out of the 5 liter bucket. If you figure out a way to do that, you have it solved. You need a 1 liter space to pour the 1 liter into. You would have to leave 2 liters in the 3 liter bucket. So if you figure out a way to do that, you have the problem solved. To do that, you need to get 2 liters into the 5 liter bucket. So you can then put the 2 into the 3 liter bucket. Here how we can achieve this. Fill the 5 liter bucket and pour 3 of it into the 3 liter bucket, then empty the 3 liter bucket. This will leave you with 2 liters in the 5 liter bucket. Dump the 2 liters into the 3 liter bucket. Fill up the 5 liter bucket and pour 1 into the space in the 3 liter bucket. So now you have 4 left in the 5 liter bucket. So this is an interesting logical puzzle asked by several companies. The expectation is the approach that you are going to follow in order to achieve the solution. In the first approach, whichever I have explained, has more steps compared to the second approach. It would be good to know both the approaches.
At a party, everyone shook hands with everybody else. There were 66 handshakes. How many people were at the party? Let me explain the solution now. Let's suppose that there are n number of people in the party. The first person will shake hand with n minus 1 people. The second person will shake hand with n minus 2 people. The third person will shake hand with n minus 3 people. In this way, n minus 1th person, that is, last but one person, will shake hand with n minus 1, which is equal to 1 person, that is the last person. Now add all the number of handshakes, n minus 1 plus n minus 2 plus n minus 3 plus so on till 3 plus 2 plus 1. If you observe this particular series carefully, this is nothing but the sum of n natural numbers, but only difference is here the n is n minus 1. We know that the sum of natural numbers formula is obtained by using the arithmetic progression formula where the common difference between the preceding and succeeding numbers is 1. Natural numbers are also called counting numbers, start from the number 1 until infinity, such as 1, 2, 3, 4, 5, 6, 7 and so on. Sum of n natural numbers formula is represented like this: n times n plus 1 over 2, where n is the last number. In this case, we know that n is n minus 1, hence formula becomes n minus 1 times n minus 1 plus 1 over 2. After simplification, formula becomes n times n minus 1 over 2. Also, we know that in the puzzle, the total handshakes given are 66. Hence, the equation becomes n times n minus 1 over 2, which is equal to 66. After simplification, it becomes n times n minus 1 equals 132. Further simplification results in n square minus n minus 132, which is equal to 0. This is nothing but the quadratic equation. After solving quadratic equation, we get n minus 12 or n plus 11 equals 0. Here, either n equals 12 or n equals minus 11. Since number of people can't be negative, n will be 12. Hence, there are 12 people in the party. Consider you are starting at A and you can move only one step up or one step right. How many different paths from A to B are possible? Let me explain the solution now. If we start at A and move towards B, we can have the following paths: R, 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 U, U, where R is right 1 unit and U is up 1 unit. There are other multiple possibilities. Few of them are U, U, R, 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 U, R, U, R, 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 U, U, R, and so on. This way of manual counting is not a right approach to solve these kind of puzzles. When grid becomes bigger, then manual approach will lead to many errors. The best way to approach the problem is through combinations approach. It is noted that every route consists of 5 moves, in which we have 3 right moves and 2 up moves. Here we can use our combination formula, and it can be represented as NCR equals n factorial over r factorial times n minus r factorial. The number of different paths from A to B can be found by finding how many combinations of 3 right moves we can have in our 5 moves. So n is number of moves and hence n will be 5. Out of n moves, 3 is always r, that is right moves, and hence r in the formula is 3. Remember, it can be solved using up moves as well. Now substitute the values of n and r. After substituting, expression becomes 5cr equals 5 factorial over 3 factorial times 5 minus 3 factorial. After further simplification, it becomes 5cr equals 5 factorial over 3 factorial times 2 factorial. 5cr equals 120 over 6 times 2, which is equal to 120 over 12, which is equal to 10. Hence, number of different paths from A to B possible is 10. Similar approach can be used to solve for other grids also. And this is the right way to solve these kind of puzzles. By following these simple steps, we can solve these kind of puzzles in less than 30 seconds. You have a 5-liter jug and a 9-liter jug. Your mother asks you to use these 2 jugs to measure 1 liter of orange juice. How would you do it? There are multiple solutions to this particular puzzle. Try to find the optimal solution. Let me explain the solution now. To start with, first fill the 5-liter jug and then pour all the orange juice in the 9-liter jug. This would leave with 4 liter of space in the larger jug and 5-liter jug is empty. Next, refill the 5-liter jug and fill up the remaining portion of the 9-liter jug. As we know already that the space remaining in 9 liters jug was 4 liters, hence you have transferred 4 liters orange juice from 5 liters jug
and 1 liter of orange juice is still in 5 liters jug. So this way we will have 1 liter orange juice left in the 5 liter jug which was asked in the puzzle. As you can see here, it can be achieved in just 2 steps. There can be other ways in which you can achieve the solution, but this is the most optimal solution. Your room has 3 switches. One of these switches is for a fan in the next room. You cannot see whether the fan is on or off unless you come out of the room. What is the minimum number of times you may go in a room to identify the correct switch in another room? Let me explain the solution now. I would go only once to the other room to find out the accurate switch for the fan. Here is the step-by-step explanation. I would turn on the first switch and keep it on for 2 to 3 minutes. Next, I would turn off the first switch and turn on the second one. I would run to the other room as soon as I switched on the second switch. Here, there are 3 possibilities. If the fan is running, the second switch is for the fan. If the fan is not running, obviously second switch is not the right switch. If the blades are rotating slowly, the first switch corresponds to the fan. It's because fan will not immediately stop when the switch is turned off. Speed will reduce gradually and finally come to stationary, and for this it takes time. If fan is not running and it is not rotating slowly, that is, if the fan is in stationary, then the correct switch of the fan is the third one. Thus, minimum number of times you may go in a room to identify the correct switch in another room is just 1.